Today we're talking about pressure. And I mean, we're all under pressure, right? Deadlines, decisions, just daily
Oh,
responsibilities.
tons of it.
But human pressure is, it's probably hard to quantify. You can't just put a gauge on human stress. But what's funny is that the pressure inside a dryer vent, that is surprisingly easy to measure.
It really is. It's actually a very precise science.
Yeah. So our goal for today's deep dive into our source document is to really unpack this. We want to figure out exactly what inches of water column actually means, how it, helps us evaluate dryer vent performance, and why these tiny invisible pressure differences matter so much.
Right. And just to give a little context up front,
Yeah.
inches of water column is a term used broadly across the whole HVAC industry. It's used anytime you need to measure really small pressure differences in air-moving systems.
Okay.
But for this deep dive, we're going to stay laser-focused specifically on clothes dryers.
Perfect. Why not just use PSI, like we do for car tires?
Or plumbing. Yeah.
Exactly. Why are we talking about water columns for an appliance that literally just blows hot air?
It's a fair question. Honestly, it comes down to scale. PSI, which is pounds per square inch, is it's just too massive a scale for the tiny pressures we're looking at inside a dryer.
Too massive. Like, how big of a difference are we talking?
Now, 1 PSI equals approximately 27.7 inches of water column.
Wait, almost 28 inches of water column just for one single PSI.
Exactly. And if you flip that around, 1 inch of water column is a tiny, tiny fraction of a PSI.
Wow. Okay, so if a technician used a PSI gauge on a dryer, the needle would barely even twitch.
Right. So inches of water column is simply the right size ruler for the job.
The right-sized ruler. I like that. But, okay, let's get literal here. Where does the water column part actually come from?
It comes from this classic, really brilliant tool called a U-tube manometer. Just picture a clear tube, right? And it's physically bent into the shape of a U.
Okay, I'm picturing it.
You take that U-shaped tube, stand it upright, and partially fill it with water. Now, if both ends of the tube are just open to the room, the water levels on the left and right sides are going to settle at the exact same height.
Because the room's air pressure is pushing down equally on both sides.
Exactly. But now, imagine you connect one side of that U-tube to a pressure source, like your dryer exhaust.
Okay, so I'm hooking a hose from the dryer vent to the left side of the tube.
Yep. The air pressure from the dryer pushes down on the water on that left side. And since the water has nowhere else to go, it gets forced up on the open right side.
Oh, right. So it's like a seesaw made of water.
Exactly like a seesaw. But here is the critical part about how we get the actual measurement. If the air pressure pushes the water down exactly 1/2 inch on the pressurized side,
Then it has to rise exactly 1/2 inch on the open side because it's the same amount of water.
yes, you've got it. So to get your reading, you don't just look at how far the left side dropped. You measure the total vertical distance between those two new water levels.
Wait, let me make sure I'm doing the math right here. So 1/2 inch down on the left plus 1/2 inch up on the right.
Equals 1 full inch of vertical difference.
Then that is 1 inch of water column.
That is exactly 1 inch of water column. It's a literal physical measurement of distance.
That is so cool. It takes this invisible force and turns it into a physical ruler made of water.
It really does.
Yeah.
But understanding how that water moves naturally begs a bigger question. What is that pressure actually being compared against?
Because we left one side of the tube open to the room, right?
Right. What's fascinating here is that we are never measuring pressure in total isolation.
What do you mean?
Well, we live completely submerged in an atmosphere. The air all around us is constantly exerting weight in every single direction.
Right, atmospheric pressure.
Exactly. So the atmospheric pressure in the room where the dryer sits provides this really convenient, invisible baseline reference.
So just to clarify, if a technician hooks up their gauge to my dryer vent and it reads 0, it doesn't mean there is 0 pressure in existence, right?
Right, absolutely not.
It just means the pressure inside the vent is exactly identical to the room.
Spot on. It means there's no difference. The instrument is basically just asking, how different is the test point from the room you're standing in.
Okay, that makes sense. So if the pressure inside the vent is higher than the room, that's positive pressure.
Yes, positive pressure. The dryer is pushing out harder than the room is pushing in.
And if it's lower than the room,
Then it's negative pressure.
Hmm.
Or, a vacuum.
got it. Okay, here's where it gets really interesting for me. Because carrying a sloshing glass U-tube full of water into a laundry room seems like a terrible idea.
Yeah, it would be a huge mess.
So how do we actually capture these tiny measurements in the field today? because the tools have to have evolved.
They absolutely have. To understand the modern toolkit, we kind of have to separate the physical tool from the method of how we use it.
Okay, let's start with the tools. What's replacing the U-tube?
Well, one step up from the basic U-tube is the inclined manometer. It still uses liquid, but it puts part of the tube at a very shallow angle.
Why angle it? Does that change the pressure?
No, it doesn't change the pressure at all.
Yeah.
But think about it, if you're trying to read a microscopic vertical height change, it's really hard to see with the naked eye.
Oh, so if you put the tube on a slant?
The liquid has to travel a much longer physical distance along that slope just to reach the same vertical height.
That is so clever. It basically stretches the measurement out so a tiny vertical difference becomes a big diagonal movement.
Exactly. It spreads that small height change over a longer distance, which makes tiny differences way easier for a technician to read.
Okay, but still there's liquid involved. Tell me we have digital versions now.
We do. Digital manometers are extremely common today. They completely replace the water with internal electronic sensors.
And they still compare the test point pressure against the room's atmospheric pressure.
Yes, exactly the same principle. But what's funny is, even though there's no water inside the digital tool, the screen still displays the result in inches of water column. It's the industry standard unit now.
So we have digital sensors, we have glass tubes. Are there any other tools? Because I feel like I've seen these mechanical dials used before.
You're definitely thinking of differential pressure gauges,
Yeah.
like the Magnehelic gauge, which is a very popular brand.
Yeah, those round dials with the sweeping pointer needle. How do those work if there's no water and no battery?
It's pure mechanical engineering. Inside that gauge, there is a highly sensitive internal diaphragm. It's like a tiny flexible drum skin dividing the inside into two chambers.
Okay, one chamber for the room pressure, one for the dryer.
Exactly. The pressure acts on that sensitive diaphragm, and as it bulges even a microscopic amount, it moves a tiny mechanism that sweeps the pointer across the dial.
Wow, so it just translates the physical push of the air into a needle movement.
Right,
Okay, so we've got this whole toolkit of instruments, but having the tool is only half the battle.
right. You need to know where and how to actually use it.
Exactly. Which brings us to the methods.
Anytime air is forced through a pipe, it creates resistance. So our source covers two distinct methods to evaluate how well the dryer is handling that resistance.
And both of these methods use pressure as a proxy for airflow performance, right?
Yes, because measuring actual air velocity in a home vent is tough, but measuring pressure is precise. And crucially, both of these methods use the room's atmospheric pressure as the reference.
Okay, lay them on me. What's the first method?
The first one is measuring negative drum pressure. Some people just call it testing the vacuum.
Vacuum. So we're measuring inside the dryer.
Yes, exactly. You take a measurement inside the dryer drum while the machine is actively running. And that drawing action drops the pressure inside the drum below the room's atmospheric pressure.
Ah,
It's a negative pressure measured in inches of water column. And if the vent is clogged, that negative number changes in a way that alerts the technician.
that is so smart. Okay, so that's the vacuum side. What's the second method?
The second method is measuring back pressure. This is measured in the exhaust duct directly behind the dryer. The operating dryer is forcefully pushing air into the exhaust ductwork, but all those elbows and the lint in the pipe, they create resistance. That resistance forces the pressure in the duct to rise above the room's atmospheric pressure.
So the air gets bottlenecked and the pressure spikes.
And that spike is the back pressure. And again, the gauge compares that higher pressure inside the duct to the lower pressure in the room.
So the drum test measures negative pressure, and the exhaust test measures positive pressure.
You got it. Both give us measurable objective insights into how easily the dryer is actually moving air. Consistency is absolutely key.
Right.
The test location, the specific range of the instrument, and this is crucial, zeroing the instrument to the room's atmospheric pressure before you test.
And most importantly, manufacturer-specific requirements for your exact dryer always take precedent.
Thanks for joining us, and we'll see you on the next deep dive.